am Cadet First Class Abigail Aristides.
And I am Cadet First Class Stephen Harold, and we are systems engineer majors working with the Warfighter Effectiveness Research Center at the United States Air Force Academy.
This year, we have been focusing on research to better understand trust in automation.
And today we are going to describe a comprehensive measurement system that we developed to assess trust in automated vehicle features using a Tesla Model X.
In 2019 alone, there were over 6 million vehicle accidents resulting in over 36,000 deaths. The National Highway Traffic Safety Association found that in over 90% of fatal accidents, human error was involved. A potential solution is to shift driving tasks to automated systems and reduce or remove human involvement altogether. Vehicle automation has the potential to significantly reduce these numbers by decreasing driver workload, correcting for driver error, or by actively performing most, if not all, driving tasks. But the nature of the driving task changes as control shifts from humans to automated systems. This shift can result in new types of human errors that stem from miscalibrated trust. A recent accident in 2018 involving a Tesla Model X highlights this issue. The human driver failed to properly pay attention and monitor the automation system due to over-reliance on Tesla's autopilot. This begs the question, how much should we ultimately trust these autonomous driving systems, and what factors contribute to this trust? To this end, we developed a 3-tiered measurement approach by combining self-report, behavioral, and physiological data to assess 3 types of trust in driving automation. Dispositional trust is related to the individual's propensity to trust an automated system, which can be influenced by factors like culture, age, gender, and personality traits. Learned trust can change over time and is a combination of prior knowledge one has about a system and new experience from actually using an automated system. Situational trust is location-based and relates to the context the automation system is being used in, making it inherently dependent on the environment and situation.
But how can these types of trust in driving automation be measured? Trust is a complex construct that can be assessed using self-report, behavioral, and physiological measures. Although important, self-report measures alone provide only a small piece of the trust puzzle. By incorporating behavioral and physiological measures, we can gather a more holistic view of how trust manifests in the real world. Behaviorally, for example, it's important to measure human automation interactions, such as turning on or off automated features, and where drivers tend to do this on the roadway. Similarly, understanding how drivers allocate attention via eye movements is critical to understanding how this changes with levels of trust, time, and location. But how do we capture these types of behaviors? A central component of the measurement system is an Ergoneers vehicle testing kit that we integrated into the Tesla. This system is a commercial off-the-shelf solution for collecting vehicle telemetry data and allows for several different sensor streams to be aggregated together. With the Ergoneers system, we are integrating CAN bus data from the Tesla, forward roadway information from a Mobileye camera, and location data from the GPS sensor. This vehicle data is combined with physiological data from the driver, specifically eye and head movements collected from Tobii eye-tracking glasses, which allow us to track how the driver allocates attention while operating the Tesla. Video data and experimental observations are used to record driver behaviors and roadway events not readily captured through the Ergoneers system and our suite of sensors, such as drivers taking their hands off the wheel or an animal appearing on the roadway. We developed a custom mobile application called the Driver Observation Tool that is shown here. To capture relevant experimenter observations and streamline coding of video data, an experimenter can log an observation by simply pressing a button to indicate frequency of a given behavior or event and is logged with a timestamp. These observations are used to validate driver behaviors and roadway events via onboard cameras, offering redundancy within our measurement approach. We developed the Driver Observation Tool using a systems engineering approach. First, we conducted a needs and requirements analysis and iterated through low and medium fidelity prototypes. After getting stakeholder feedback, we developed the final research tool prototype. This prototype was then tested using both naive users and members of the research team to validate the tool's ease of use and efficiency. The final research tool allows for easy event logging, about 3 seconds between button presses, and has high usability. Ultimately, this work will provide an approach to measuring trust in future experimental paradigms and inform our understanding of how trust in state-of-the-art, commercially available automated vehicles is potentially built, maintained, lost, and regained over time in real-world settings, with the goal of improving the design of user interactions with autonomous systems.